This is the higher level problem type for momentum and impulse. In standard level, we learned about momentum and impulse as it relates to an object that has changing momentum due to a changing velocity. But in this situation, we're going to look at just change of momentum as a whole. So we really need to start looking at change of momentum as the change in both mass and velocity. The simplest way to see this is like if we had a final mass times some final velocity minus an initial mass times some initial velocity. And this would solve for the total change in momentum. Another way of writing this, though, because to kind of keep with the context, would be like this, yeah? But in the higher level problem type, we're going to look at not a changing velocity, but a changing mass. So we're really going to say, well, what if the velocity is constant? Let's just look at how much force could be applied if we, change the mass. The way that we could see this would be like if you're on a skateboard and you like remove mass from your skateboard, like like you're holding a gallon and you toss the gallon behind you, a gallon of water or something. You're going to go faster because you're pushing something away from you. So another situation which shows up is like rockets, where some rocket fuel, is pushing gas out, and there's some mass being released, so it's applying a force. In this case, we have a toy rocket of mass 0.12 kilograms containing 0.59 kilograms of water. The space above the water contains high pressure air. The nozzle of the rocket has a circular cross section of radius 1.4 millimeters. Okay, that's going to be important, and it's in millimeters, so I need to identify that. That's 1.4 times 10 to the negative third meters. When the nozzle's open, water emerges from the nozzle at a constant speed of 18 meters per second. The density of water is 1,000 kilograms per cubic meter, and we need to show that the volume of water ejected per second from the nozzle is 1.1 times 10 to the negative fourth cubic meter. I imagine we need to find the volume of water ejected per second so that we can find how much mass is ejected per second, and then we'll relate that to a changing momentum. And we should know that if we are pushing water out one way or pushing some momentum out one way, that we should gain that equal momentum in the opposite direction. A situation like this would be if you're holding, like a liter of water and you're on like a skateboard and you toss a liter away from you, your skateboard and you might move the opposite way. So let's see how we can find the volume ejected per second. Well, the volume of water must be coming from the nozzle, right? And it should look like something like this. Like if we imagine the water is being shot out kind of like as a water gun. So how can we find out how much water is ejected per second? Well, we do know, and let's make this a little bigger. We do know the radius of this cross-sectional area, right? That's your R, right? That's your R right there. But how do we know this length? Well, we need to find how much is ejected per second. We do know how much water is being shot out per the speed of the water being shot out. So actually what we do know is we know how much is traveling this length per unit time. Length per unit time is the same as velocity, and we know what this velocity is. That's 18 meters per second. So we can imagine that there's some volume of water being ejected per unit second that's dependent on the cross-sectional area of the nozzle and the length per unit time, the distance per unit time that the water is traveling out. So we need to find this volume in here. So that's equal to pi r squared, which is the cross-sectional area of the base, times the velocity. And that's going to give us our volume per unit time. So if I plug this in, I have pi times 1.4 times 10 to the negative 3 squared times velocity, times 18. If I plug this into a calculator, I get 1.108 times 10 to the negative fourth. So that's like 1.1, actually it's more like 1.11 times 10 to the negative fourth. And that's meters cubed per second. Right, pi r squared is meters squared, velocity is meters per second, so that's meters cubed per second. And we have our volume per unit time. So I might write volume like that, per unit time. Okay, so what is the upward force acting on the rocket due to the propulsion of water? So we said, well, the upward propulsion is going to be dependent on how much mass we're pushing out. So we need to not just find volume per unit time that's pushing out, we need to find mass per unit time that's pushing out. So let's just do that first, and let's see how we can use that in our equation. So we have 1.11 times 10 to the negative fourth cubic meters per second, and that's volume per unit time. I know that my density, which often is written as like rho, and that's 1,000 kilograms per cubic meter. And let's just stop right there and see if there's anything else we need. Yeah. So let's find, we plug these two together, and if I multiply them together, I get 1.11 times 10 to the negative fourth meters cubed per second times, let's put it actually like this. This is called dimensional analysis, and super easy to use, this technique of dimensional analysis. Times 1,000 kilograms per meters cubed. When I set it up like this, I can see that my meters cubed cancel, and I end up with seconds in my denominator in kilograms in my numerator. And that should give me, well, still 1.11 because I'm just multiplying by 1,000. 1.11 times 10 to the negative 1 kilograms per second. Okay, so it's kilograms per second. That's mass per unit time. So let's go back to my equation. F average times change in time is equal to, change in mass times velocity, because our velocity is going to be constant because the water is being ejected at a constant rate. If I divide by time, I get F average equals delta M over delta T times some velocity. Now, really what we're looking at is if this is the rocket, let's say this is the rocket, this is going to feel the force upward because the water is being ejected downward, right? So we're technically, when we're calculating this is what we're finding, and then we're saying, well, that equal and opposite forces due to Newton's third law, that must equal to the force acting on the toy rocket going upward. So this is our logic to this. So I have my mass per unit time, that's 1.11 times 10 to the negative 1 kilograms per second, and multiplied by the velocity, which is still 18 because that is the velocity of the water being ejected. And that should equal our F average. And if we do that, that's times 18. And I get about 2. It's around 2.0 newtons. And this is the force that's going to be acting on our rocket. Now the next question that I can push further on, and this is where we want, is, well, if it's acting on our rocket, is it acting on our toy rocket that has a mass 0.12 kilograms, or acting on the water as well? Because the water is ejecting, but it's not ejecting very fast, right? This is like 1.11 times 10 to the negative 1 kilograms. That's like 0.111 kilograms per second. So after 1 second, it should be like, 0.48 kilograms of water left. After 2 seconds, it should be like 0.37 kilograms of water left. So when we come to class, what I'm going to ask you, when you come to HL class tomorrow or on Friday, I'm going to ask you, what is the acceleration time graph look like for this rocket? That's going to be our warm-up question. So I will see you in class.